Hello again, and welcome to the third video for topic 1 for week 9. This is going to be a bunch of questions relating to temperature scales, and thermal expansion. As usual, we'll jump over to the slideshow, but we'll be using the document camera mostly for this one since it's all questions. Temperature and thermal expansion, we'll go straight to questions. First one, fairly simple one, just relating to temperatures in Fahrenheit and Celsius. Many Americans' discussions involve temperatures in Fahrenheit. Recipes, medical notes, weather, and so on. You'll often hear talk of Fahrenheit. This is just a little test for you, not a test, it's practice for you to convert temperatures between the two scales. So these three temperatures are given in Fahrenheit. We want to convert them to Celsius and then into Kelvin. So if you can't recall the equation for Fahrenheit to Celsius, remember that the intercept adjustment is 32. You need to add 32 onto it, and the scale ratio is 9/5. That's the step size ratio. So you've got 9/5 there. As I keep repeating, try these problems. Don't just watch me and go, oh yeah, I could figure that out. Have a go at this question before you watch my solution or before you read the next slide, and see if you can actually get the result out. It's the only way to really know that you can solve the problem. So the equation, as I just said, is Fahrenheit temperature is 9/5 of the Celsius temperature plus 32. Since we've been given Fahrenheit, we want Celsius, so we actually have to rearrange this. So we have to take 32 off both sides. So 9/5 Celsius is equal to Fahrenheit minus 32. And then we need to rearrange by getting rid of this. So we multiply both sides by 5/9. Right? If we multiply by 5/9, that'll cancel those out. So that means that we have 5/9 times that thing. I'll write that a bit clearer just to be nice and obvious. 5/9 of TF minus 32. So at this point, if you haven't done the calculations, if you didn't get that rearranging right, pause the video again, or do now if you haven't yet paused it, and do these three calculations. At this point, it's just practicing using your calculator, but I'd still like you to be able to do that confidently. So we've got the first one was it body temperature? Body temperature of 98.6. So body temperature of 98.6 becomes 37 degrees Celsius. Then we've got, what was the other one? Oven setting. So an oven at 360 degrees F becomes 182.2 degrees Celsius. Probably around about 180 Celsius is what you'd set your oven to. And the last one is a comfortable room temperature of 70 degrees Fahrenheit. Becomes, I realize I hadn't written the other ones for those, but I'm sure you can all manage, becomes 21.1 degrees Celsius. So around 21 degrees Celsius for 70 degrees Fahrenheit. To convert to Kelvin, we just add 273. I haven't done that on the slides, and I'm not going to do it here. I'm sure you can all add 273 to those numbers without issue. Right, next question. Determine if there is a temperature at which both a Fahrenheit and Celsius thermometer would give the same reading. Right, so this you can start to think about it in terms of the physics. What does it mean for the two scales to be the same? But essentially, it's actually just a mathematics problem. So I'm always going on about being able to identify the difference between maths and physics, but this sort of thing is still a useful exercise to be able to make sure you can do the maths and to think about what that means in terms of the physics, right? In this case, doesn't mean too much in the physics, just means that there is some point in our scales where they overlap. And that's always going to be true if you've got two lines that have different slopes. For Celsius and Kelvin, they've got the same slope, same step size. They're never going to intersect, they're never going to overlap. You're never going to be able to say that you've got the same temperature for Celsius and Kelvin. But Fahrenheit, it's got a different slope, so it will have an intersection with Celsius at some point. So the answer is going to be a yes, it does have a position where it can overlap. So how do we find that? Well, we just use some math, as I said. We just need to use some algebra. So let's take that same equation again. Temperature Fahrenheit is equal to 9/5 of the Celsius temperature plus 32. That's our conversion equation. And what we're saying is, can we find a temperature where these two numbers are exactly the same? So let's call them both x. Let's say that we've got x for both of them. So what we have is that x is equal to 9/5 x plus 32. And now it's just algebra, just rearrange that to figure that out. So times everything by 5 might be a good place to start. 5x is equal to 9x plus 32 times 5, which is 160. 3 times 5, 150. 2 times 5 is 10, 160. And then we can figure out which way we want to do this. I'm going to move the x's over here. So minus 9x gives us minus 4x equals 160. So x is equal to 160 divided by negative 4 or negative 40. So x is equal to negative 40 degrees Fahrenheit and degrees Celsius. It is the one temperature at which Fahrenheit and Celsius are the same, negative 40 degrees of either. Next question. Copper coin. How many atoms are in a copper coin that weighs 3.4 grams? The mass of copper is 63 atomic mass, so this is per atom. One atom of copper weighs 63.546 U. Remember that atomic mass unit from the first video. How many atoms are there in the coin? So this, if you remember the example where we talked about a big brick of copper, a 1 meter cube of copper, this is almost just the first half of that, right? It's just a practice for you to have a go at that again. So if you remember that example, this is a very similar process, but now rather than having 1 cubic meter of it, we've only got 3.4 grams. So we don't need to worry about the density, and we're not worried about the spacing, so we don't need to do that whole geometric reasoning afterwards either. We're just looking at the mass into number of atoms calculation. So as I said, similar to what we did in that example. So hopefully you all had a go at that now. I will grab a new sheet of paper. And let's think this through. So we've got 3.4 grams. That's our total mass. We've got the atomic mass of copper. So mass of one copper atom is equal to 63.546 U. And so for that, you now need to remember how much a U is. What's an atomic mass unit? And that is, I'll write that, I'll just do it up here. U is equal to 1.66 times 10 to the negative 27 kilograms. So that means we have 63.546 times 1.66 times 10 to the negative 27. And that gives us 1.055 times 10 to the negative 25 kilograms. So each atom has a mass of that many kilograms. 1.055 times 10 to the negative 25. You can see why we stick with U. 63U is a lot easier, or 63.5 U is a lot easier than 1.05 times 10 to the negative 25 kilograms. It's just cleaner doing it this way. Yeah, but obviously you have to be able to convert back, which is the point of this question. So if we've got a total mass of 3.4 grams, and each atom weighs this many grams, or this many kilograms, how do we figure out how many atoms there are? Well, we just divide it. Now you have to remember that this is in grams, so we need to convert. So 3.4 times 10 to the negative 3 kilograms. So we just divide it. So the number of atoms is equal to 3.4 times 10 to the negative 3 kilograms divided by, so that's how much total mass, and this is the mass per atom, 10 to the negative 5 kilograms. Now what you could do, if you weren't sure about this formula, which way around to divide these or whatever, is to think for a moment about what this term actually is, the mass of one copper atom. You're saying it's that many kilograms per atom. So while atom isn't actually a unit, right, it's a count, it's how many things we're counting, you could still write it in if you want, because then you'd see that you'd have kilograms over atom. Right? And so this way, kilograms will cancel, and you'll be left with 1 over atoms, which is just atoms. right? So you'll be left with some number of atoms. If you did that the other way around, you'd end up with 1 over atoms. You'd have something per atoms, and that doesn't make any sense for what we're looking for. Now you just use your calculator, and hopefully you get out the same value I did, which is 3.22 times 10 to the 22 atoms. So that is how many atoms of copper there are in a 3.4 gram copper coin. Next question. We're now moving on to some expansion, thermal expansion. This one is volumetric expansion. We're talking about a steel gas tank of a car. It's 70 litres capacity, so it's quite a big gas tank. And it is filled to the brim with petrol. It's absolutely full of petrol, and it's at 20 degrees Celsius. But then the car sits in the sun and heats up until both the tank and petrol are at 40 degrees Celsius. How much petrol will overflow from the tank? So obviously a few assumptions. One is that the opening for the tank is right at the top, so that the overflow will come out the top. The other one is that it's open, so that the petrol can overflow rather than expanding and forcing the steel tank to be under tension or under stress. So those are our little assumptions. But now we're going to do that calculation. We've been given the volumetric coefficients, or the volume expansion coefficients, beta for steel and for petrol. You can see they're both given in Kelvin to the -1, but remember, Kelvin or Celsius doesn't actually matter because we're talking about a step size. And the other thing that you'll need to remember is 70 litres is going to, we need to think about it in terms of volume units. Actually, that's something I didn't talk about in the lecture. Because we've got delta V and V on different sides of the equation, it actually doesn't matter what units you're in as long as you're in the same one on both sides. So you need to decide whether you're going to stick in litres and leave it as 70, or whether you're going to change it into cubic meters, in which case 1 meter is 1,000 cubic meters, or go into some other volume unit. Doesn't actually matter as long as you remember that the delta V and the V are going to be the same. The change in volume and the volume are going to be the same units. Right, so let's write out what we know again. We've got an original volume is equal to 70 litres. We've got beta for steel is equal to 3.6 times 10 to the -6 per kelvins. And beta for petrol is equal to 950 times 10 to the -6 per kelvins. So you can see already 3 times 10 to the -6, 950. So the petrol is going to expand a lot more than the steel will, so we do expect it to overflow. And we've got the initial temperature is equal to 20 degrees Celsius. Final temperature is equal to 40 degrees Celsius. Therefore, the change in temperature is equal to 20 degrees Celsius, or Kelvin, right? It could be Kelvin as well because we're into a step size now. These aren't Kelvin. You'd have to add 273, but the step size can be Kelvin, can be either or. So how much will overflow? Well, first of all, we need to know how much each of them would expand by if we just let them expand completely. So the steel, change in volume for steel is going to be beta V naught delta T. So this is for steel. They both have the same original volume and they both have the same change in temperature. So beta is the only thing that's changing. So the change in volume for steel, using this value, 70 litres, 3.6 times 10 to the -6 per kelvins, and 20 Kelvin or degrees Celsius. That gives us a change in volume of 0.050 litres. So that's how much bigger the steel tank gets. It gets bigger by 5%, 5% of a litre, 5/100ths of a litre. The change in value of the petrol, exactly the same thing, but now for petrol. So we're just using the 950 term for beta, still the same volume, still the same delta T. And that gives us 1.33 litres. Right. So the petrol is going to expand by that much, but the tank only expands by that much. So 0.05 of this will be able to stay in the tank because the tank is now bigger, but the rest of it will overflow. So the overflow is going to be 1.330 minus 0.050, which is equal to 1.325. No, it doesn't. 1.330 minus 0.005. Either I've done that calculation wrong or I've done this one wrong in the slides. So one of them is incorrect. But of course, that 5 is in this place. So it would be 1.280 litres would overflow. You all can double check, right? I've made a mistake in one of those on the slides, so you can double check that. And if that's correct, then this is the answer. But if that was the actual answer, then this is incorrect. So double check those for me and convince yourselves of which one is the right one. All right, here we go. Next question, getting through these questions. The next question is an aluminium bar. It's at the desired length when it is at 18 degrees Celsius. How much stress is required to keep it at this length if the temperature increases to 35 degrees Celsius? So this is what we're talking about. It will want to expand or want to get longer, but we're going to force it to stay at that length, and we want to know how much stress that results in. We've been given all the information we need, 18 degrees C up to 35 degrees C. So these are our initial and final temperatures. That gives us our change in temperature. We've been told E, Young's modulus. We've been told alpha, the coefficient of linear expansion. Remember that the actual length doesn't matter because the change in length is proportional to the original length for the temperature expansion. And then the stress calculation, the strain, is proportional to the original length as well. So the original lengths cancel out. And we ended up not needing to know the length. So we don't need that. So we've got all the information we actually need. And there's not a lot to do with this one other than chuck all the values in and do our calculation. So it's a pretty math-heavy question, not a very physics-heavy question, but obviously it relates to a physics scenario, and hopefully you're still all keeping in mind how all these values and things interact. So we've got initial temperature is equal to 18 degrees C, final temperature is equal to 35 degrees C, therefore our change in temperature is the difference, which is what, 17 degrees C, I think. Yep, 17 degrees C, or again, that can be Kelvin now. We've been given Young's modulus is 70 times 10 to the 9, and we've been given alpha is 25 times 10 to the minus 6 per Kelvin, and newtons per square meter. Right, so we've been given all of that information, and we just have to now plug it into our formula. So you'll remember that stress is equal to E alpha delta T. So now just multiply those three things together. All we had to do was figure out that change in temperature, and then we plug the rest in, and you should get out 2.98 times 10 to the 7 newtons per square meter. And at this point, it's a good reminder to double check the units. We've got alpha and change in temperature, Kelvin and minus Kelvin, Kelvin and inverse Kelvin rather. Those cancel out. We're left with E, which is Young's modulus, newtons per square meter, and that's what we want for our stress because it's a form of pressure, newtons per square meter. So that's all good. Those units are happy. And I think this may be the last slide, the last question. There may be one more, I can't recall. Probably the last one. Question, a rod and a ring. A steel ring with flat edges sits upright. Rods of different materials are placed inside the ring. Which of the solids listed in the table on an earlier slide will eventually touch the top of the ring as heat is applied? So if we put that ring in some kind of chamber where we can change the temperature, we put the rod inside it, standing vertically like it's shown. We want to know which materials will eventually hit the inside of that steel ring as we heat both of them up. So both of them are increasing in temperature. They're both going to expand, but which materials will actually hit steel? So we'll go back and we'll find that slide of all the materials, and we'll just talk about that for a moment. Where are we? Expansion coefficients. Here we go. Here's a bunch of solids with different expansion coefficients. We've been told that we have steel for our ring with an expansion coefficient of 12 times 10 to the negative 6 per kelvins. That means that for an object placed inside it to eventually hit the inside top of the ring, it must expand faster. It must expand more with every degree Kelvin, every degree Celsius step than the steel does. And so that simply means that its alpha must be bigger than steel's. So all we're looking for is which materials here have alpha greater than steel. We've got aluminium is greater, brass is greater, copper, gold, lead, they're all greater, right? So they're all greater than steel's 12. So they will all collide with the inside of the ring. Glass won't, quartz won't, concrete and brick won't because it's about the same. So that means that it will never actually expand enough to overcome the steel expansion, and marble won't. So the metals all will, the other objects, glass and quartz and concrete and marble, they all won't. So that's the entire question. That's all we had to do. So we'll just jump in and we'll check here. That, as we've said, those ones all have larger alpha. So that's a bunch of questions. As I said, I wanted to include quite a few just to really drill home some of these concepts, hopefully get you all thinking about temperature, what it means in terms of what's going on at a molecular level, and that will pave the way nicely into the next couple of lecture topics.